writing.
Yeah, it's called Dr. Collins.
It's October, and I just fucking hate it.
Wake me up when November ends. Restart the game.
That's how this time of year always goes. All right. Back on track. Now we're going to talk about the convection part. Okay. Minus 3 over 4ac. Minus 3, 4ac. This is just a number. Times kappa rho over t cubed. Times dl times L over 4 pi r squared, or 1 minus 1 over gamma minus 1 minus 1 over gamma times mu mh over k times gm over r squared. Mu and h over k times g m over r squared. Okay. So these four differential equations define our 5 primary unknowns: p, mass, luminosity, temperature, and density. So we have 5 primary unknowns, 1 independent variable, rho, r, and then some other things that we need to talk about. So L is a free variable. Kappa is something you look up. Let's talk about epsilon. So epsilon is the energy production rate. So epsilon is in ergs per second. So this is what we're going to talk about today, is where does this come from? Oops.
And the one under the epsilon, that's just L over 4 pi r squared underneath epsilon on.
Yeah, that's L over 4 pi r squared.
Okay.
Well, that works bad. That's better. Okay. So let's talk about epsilon. Do you have a question?
Oh, what is the M? What is the subscript of the M?
Where? This?
The mu?
Oh, this is mu mh. This is the mass of the hydrogen.
Okay.
So there's this mu mh over k is a thing that shows up a lot, and it's just the reduced mass of it's just the effective mass of the particle. So this is the same thing that shows up in a lot of other places. Okay, so let's talk about epsilon. So we're going to talk about what we want to do is write I got to look off the book because there's details that I'm going to forget. So we have our reaction rates. What we want to write the energy production. We're going to write the energy production for a different process as some number, which we're going to call epsilon naught. Okay, and this comes out of quantum mechanics, and I don't know how to compute it right now. So there's some magic that comes. So this is epsilon naught, which is like the dimensionless scale of the energy production rate for the process. And then you have density to some power alpha and temperature to some power beta. And the reason that we need to write it in this manner is because it makes it easy to deal with and easy to understand. So now we just have some number that we have, and then we have the density and the temperature, which are what the star is going to do. And then there's a couple other factors in here. So there's some other stuff that will come up as we need it. But basically, we're going to write all our reaction rates as density some power times temperature to some power.
What are the squiggles?
I was just talking.
Is that a negative beta or just a beta beta?
Just a beta beta. That's the tail on the beta. Okay, so I'll come back to that in a second. I'll come back to that. So epsilon is going to be some epsilon naught times rho to the alpha t to the beta. And then there's some other stuff that will go in there that I'll talk about in a second. So now we need to talk about what does the energy production actually look like? in some kind of detail. So we talked about tunneling, right? Oh, and the book does some cute stuff with tunneling that you read, but I didn't. But I'm not going to go through. Was that? Yeah, it's delightful. So okay, so what we need to do is take two protons and smash them together and get a helium. Well, actually, we need 4 protons. And we get a helium-4. So okay, this notation, 4, 2, this. What does this mean? So what is the little 2 on the bottom? Is anybody familiar with? No.
Number of protons.
Number of protons. And what's the upper one?
Atomic mass.
Which is the number of
Protons and neutrons.
protons and neutrons. Okay. So this is protons and neutrons. This is just protons. And this is what we call it, which is redundant to the number of protons, but that's all right. It's useful to keep track of things like that. So we have a number of processes that we're going to talk about. So we're going to talk about the PP chain. Let's all get a good giggle out. Right. So we got the PP chain, and we've got several variants of that. We have number 1 and number 2, and number 3. Don't ask what number 3 is. No, I'll tell you what number 3 is. It's another variant. Someday over beers, I'll tell you a story.
So beers on Friday?
This is on. Yeah, I mean, there's no class on Friday, so.
Well, if there was beers, how would you feel about Bruce?
Oh, pretty good generally. Okay, so we're going to talk about the PP chain, we're going to talk about the CNO cycle, and we're going to talk about the alpha process, the triple alpha process.
That sounds like a sorority.
Like what?
That sounds like a sorority.
Oh, alpha, it sure does. Or a fraternity. I mean, they're the ones that are more likely
It's
to
already
focus on
delta,
alpha,
delta,
right?
delta.
Okay, so proton-proton chain. So this is the most important one because it's the one that happens the most often. So you don't just get 4 things that smash together to make 1 helium. So the book writes down the kind of basal constituent relation, which says 4 times 1 hydrogen goes to 4, 2 helium plus how many positrons? 2 positrons plus 2 neutrinos, and I think those are antineutrinos. No, they're real neutrinos. They're real neutrinos because it's a positron. Does that make sense? So no, does that make sense to anybody else? So okay, how many? This is a reaction. So I start off with 4 protons on one side. How many electrons do I have on the right-hand side?
2.
0. I said I start with 4 protons. I didn't say I start with any electrons.
You said right-hand side.
I'm sorry, it's right. Jesus Christ. The ADHD is cranked up all the way to 19-point squirrel today. So I start off with 4 protons. How many electrons do I start off with? 0, right? So how many electrons do I need on the other side? Also 0. So this is an anti-electron, and this counts as an electron. It takes the electronness, but not actually an electron. It's a neutrino. So it takes it gets to count as a neutrino. So I get a neutrino and a positron, which means no change in the lepton number because I go up by 1 with the neutrino and down by 1 with the positron.
And is that E a subscript next to the nu, or is
yes.
that is?
Yeah, that is nu sub E because it's an electron neutrino. So there's 3 kinds of neutrinos. Yeah.
So is that 2 of the protons turning into neutrons and setting off 2 positrons?
The net effect is yes. So I have 4 protons in the beginning. I have 2 protons and 2 neutrons at the end, right? And that process of making neutrons spits out positrons and neutrinos. But we don't ever touch the neutrons. It all happens in the nucleus. So we're not literally taking a proton and an electron and smacking them together and making a neutron and putting that in the thing. It all happens at the same time in the process. So let's talk about what the process actually looks like. So this is the bulk. So really how I should write this is, I'll write it over here. 4,1 hydrogen goes to, actually, huge box of stuff. So 4 hydrogens go into my box of stuff, and out of my box of stuff gets a helium-4 plus a positron, 2 positrons, plus 2 electron neutrinos. So let's talk about what goes into this stuff. So this is a 3-step reaction. So the first step is hydrogen plus hydrogen gives me what? What do you think a hydrogen and a hydrogen is going to give me? I just have 2 protons. A helium.
Helium-2.
Helium-2. Just that doesn't. You can't make that.
Deuterium?
You can't make. You can make a deuterium. You can't make 2 protons by itself. Helium with no neutrons doesn't exist. It can't.
So it spits off the charge and becomes deuterium.
Yeah, so one of these guys, in the process, one of these guys turns into a neutron, and I'm left with 2, 1, H. This is a deuteron. It's a helium, it's a proton and a neutron, plus a positron, and a nu. This is the first step, is making a deuteron. But that's pretty cool. What can I do with a deuteron?
Make hydrogen.
Smack 2 neutrons.
So 2 deuterons. What does that look like? Actually, do I have enough color yet? Yeah, sweet. There's a red one. Protons are red and neutrons are blue.
Fun facts.
So here I got 2 protons. I got a proton and a neutron. And electrons are yellow, but I don't have any yellow chalk. What we're getting is as a helium-4. And that has 2 protons and 2 neutrons. So hey, it looks like I could just take 2 of these and smack them together and make a helium-4, but it doesn't actually work that way. The most common way is you start with your deuteron. And I smash it into a proton. And what's a deuteron and a proton going to give me?
Triton?
It could give me a triton. It could give me a tritium, which is 2 neutrons and a proton. So that's one possible channel. The other possible channel is it could give me a helium-3. Plus, again.
So what happens if it makes a tritium? Because it's like this is a random reaction.
Yeah, if it makes a tritium, then that tritium will probably just decay. I'm not 100% sure. So that's a question for Ingo Wiedenhofer.
Yeah. Okay.
Or hopefully somebody who really knows the nuclear astrophysics. Nuclear astrophysics is like a dude I met in college once. It's not something that I spend a lot of time with. So
whole different. Fields.
So there's a lot of questions like that I just don't know. There might be something cool. So then I take a helium-3 plus another proton, and that gives me a helium-4. But this is a really rare process. So that actually doesn't happen very often. Mostly because the helium-3 is really short-lived. So this is rare. So let's not think about it for a second. The most common process is I take 2 of these helium-3 and I smack them together and I get a helium-4 plus 2 protons.
Hydrogen or helium?
Up, E. So let's talk about energy for a second. So why does this process give off energy?
Because of the massive
Binding energy.
Was that
Binding energy.
binding energy of what?
The two elements.
Yeah, so the deuteron and the proton are bound together, or the neutron and the proton are bound together by nuclear forces, by the strong force. That strong force is negative, so it adds to the overall mass budget, and mass goes down of the combined object. And that comes out as energy. And that's the same thing that happens with each of these processes. So there's a homework problem, work out what how the energy looks for each of these. How much energy do you get for each one of these processes? Oh, I should have asked which one gives you the most energy. That would have been an interesting question.
Still do it.
I can still, well, it's up. I mean, I'm not going to change
Well,
the
no one
homework.
started it.
Was that?
I'll tell you that right now.
Yeah, because it went up like an hour ago. Okay, so that's the, oh shoot, I shouldn't have erased all that. So this is PP1. So PP1 is proton plus proton gives me a deuteron plus a positron and a nu. And then D plus P gives me helium-3. And then 2 helium-3s gives me a helium-4 plus 2 protons. Is there other things that come out of that? No. So, yeah.
Is that P plus P, or what is the D?
D is a deuteron.
And is that
That's a neutron. It's a neutron and a proton.
and then is that a positron and a neutrino?
This is a positron and a neutrino. So this is what I just wrote down. So this is PP1, but sometimes other things can happen.
What happens to the positron and the neutrino?
The neutrino leaves,
Oh.
because that's what they do. They just leave, because they don't have to interact with anything. So they just nope out. There's a loss of neutrinos. The positron annihilates basically immediately with a free electron. So you get another. So this positron is an additional source of energy. So that's a really good question. So this positron will also provide some energy, but it's not taken into the energy budget.
Does it just make more light
Which?
when the positron?
Yeah, it makes more photons, and the photons heat stuff. So it makes more heat.
Okay.
Do we just assume that all of these atoms are naked, just nuclei?
Yeah,
Without
everything's
photons?
ionized.
Okay.
Why is everything ionized? Because the temperature's like 10 to the 7th.
Yeah.
So when you work through the Saha equation, you'll see that the ionized state is the common one. Oh, that's a good midterm problem. Okay, so these two things happen very quickly, and they like to happen. This is most common, but you can have another thing that could happen. So this always happens, and then this is one choice. Another choice, oh, it's so much more complicated. The other choice is my helium-3 could combine with a helium-4 and make a beryllium-7. Beryllium-3.
For this one, you're saying that the first two things already happened in the line from there?
Yeah, that's right. That's right. Thank you for clarifying that.
We gained a proton somewhere?
No, I'm looking at the wrong thing. As I said before, the ADHD is all the way up today. This is 4. This is beryllium. I knew it was beryllium, and then I looked at the wrong line, and it was wrong. Plus a photon. So we can keep making bigger things. So this helium-3 came out of here. So we can, if we pack it onto a helium-4, then we've got this beryllium. What's the beryllium going to do? Beryllium's going to decay. So this just decays to boron. No, to lithium. Lithium-7. Plus an, maybe. This has got to capture an electron. So now I've got a lithium. We're going to pack another hydrogen onto that. So now we're going to take our lithium plus a hydrogen, and this is going to give us two helium-4s. Yeah.
So that capture is only spitting out a neutrino?
Well, it captures an electron and it spits out a neutrino.
Okay.
So this positron is on the right-hand side, and this positron is on the left-hand side.
Yeah, is it capturing its own electron?
No, they're free electrons.
Oh, they are.
Everything's ionized. So that we just have
Okay,
a
right,
nucleus,
right.
yeah.
Oh,
That's an interesting
is
question.
that just beta decay?
Yes.
Yeah, this is a beta decay, that's right.
And there's always neutrinos that are trying to beta decay.
Yeah, that's right.
Okay.
There's always neutrinos that are beta decay. And then there's a third channel, which is why I was trying to write a beryllium. So you can go from here to here, or you can go from here. This beryllium adds a hydrogen and turns into boron plus a photon. And then this boron caps into 2 helium. No, the boron decays into a beryllium, sorry. Now we have the right number of protons and the right number of neutrons. And this requires a neutron to be converted into a proton to be converted into a neutron. So what do I have to get out? I have to get out a positron plus a neutrino. And then the beryllium-8. Now I've got 4. I've got twice 4 and twice 2. This just turns into 2 helium-4. Okay, so that's the whole proton-proton chain. And there's 3 ways for it to go. So you've got P plus P gives D plus E plus nu, and then D plus P gives a helium-3, and then you can take 2 helium-3s and get your 2 helium-4s plus 2 protons. Or you could take your helium-3 and add a helium-4, and that gives you a beryllium. And then the beryllium decays into lithium plus a nu. And then the lithium plus a proton gives you 2 helium plus a nu. Oh, so you've got this, and then this can go to here, or it can go to this last chain, which I'm not going to bother rewriting. So we've got this kind of complex chain of possible choices, and at each point where you have a choice, you have a branching ratio. Which is the fraction of events that go into one channel or the other. Does that make sense? So mostly we're just packing stuff together. But you can't pack 4 things together because that's never going to happen.
Is that all 3? Like PP1, PP2?
Yeah, then there's some stuff that I didn't write. So there's a third one that you can copy. I can rewrite it if you like. But
Is that what that is?
that's this stuff here.
Okay.
So that's the proton-proton chain. It is the dominant form of burning. And
Oh, this is just
the production rate, this is the important part.
These are PP 1, 2, and 3. That's what those three are. Or
Yeah, that's PP 1, 2, and 3.
Okay.
And the proton production is yeah, rho t to the fourth. Rho t6 to the fourth. Times a couple other things that are necessary for being real. So epsilon naught, x squared, and then a couple of constants.
Is this a different epsilon than last class?
This is this epsilon that goes in here.
The epsilon we were confused about last.
Yeah, that's this one.
That's a,
Yeah.
okay.
So you're not wrong. It's not a constant, but it also isn't a free variable because it's made of other things. I have an equation for it. already.
It has to do with the nuclear reaction.
Yeah, but it's just a function of density and temperature. So I can erase it as a variable and just write down temperature and density. So it's not a free variable because that's what I'm
Cool.
So what's the subscript next to temperature?
What's that?
What's the subscript on temperature?
6.
6.
What's that? Do you think?
There's 6 of them.
There's 6 of them. This is shorthand for temperature divided by 10 to the 6 Kelvin. You'll see this a lot. So what do you think T9 would be?
10 divided by.
Millions of Kelvin. Okay.
And then X is just some
X
stuff.
is the hydrogen fraction. So then there's a couple other things that go into that. When you read the thing, there's going to be some numbers that come from the details, but we'll set them all to 1. The important part that I care about is that this goes like T to the 4th. So as I go out in my star, the temperature goes down, the burning rate, the energy production rate goes down like T to the 4th, which is pretty fast. Not as fast as CNO. So we'll talk about CNO. I'll just write it here for that.
Sorry.
Yeah.
So for the units of epsilon p, do we use that unit of 10 to divided by 10 to the 6?
The units for this,
Yes.
or when you're plugging in numbers?
When we're trying to calculate the proton epsilon, do we plug in the original temperature? Do we convert it to the value of T6?
Think about this as just shorthand for your temperature divided by 10 to the 6 Kelvin.
And that's all raised to the 4th.
And then that's raised to the 4th. So you plug in the temperature however you want.
Okay.
Dividing it by 10 to the 6 Kelvin is going to force it to be a Kelvin and make sense, right? So it's in units of 10 to the 6 Kelvin. But if you write it like this, so if you write it like this, then this is millions of Kelvin. If you write it like this, then you can use the temperature. So just think about it like this. This is the easiest way to go.
And so the energy for each PP process or chain 1, 2, and 3 have a different X, and that's the ratio of hydrogen.
They have a different epsilon naught.
Okay.
X is the fraction of hydrogen.
Fraction
And
of that.
and that depends on the star, not on the nuclear burning.
Oh, fraction of hydrogen to all other
To
stuff.
all other stuff.
Okay.
I didn't get into those weeds too much because I didn't need them at the time. Okay, let's talk about CNO. CNO is cool. Well, maybe we should talk about triple alpha first because that's how you get carbon in the first place. So once you have some carbon, which we'll talk about where you get carbon in the first place, you have this thing called the CNO cycle. And this is important. All life on Earth is made out of
Yep.
carbon, nitrogen, and oxygen, right? And hydrogen. It's because it's made so readily in stars. Also, they're all related. So where are CN and O? So carbon is 6, Nitrogen is 7 and oxygen is 8 protons. So the way this works is we take a carbon, we pack on a proton to get a neutron, we then pack on another proton to get a carbon, and then to get an oxygen, and then an alpha particle calves off the oxygen, and I'm left with an alpha particle and a carbon. Right? Now it's got to be a 4-step process because the alpha particle that I'm getting out has 4 particles in it. So I've got to pack on 4 protons into this process and have to convert some of them into neutrons. So let's go through the first leg of this dance, and there's 2 legs of this dance. So the first bit, you start with carbon 12, 6, C, and you add a proton, and that gets you nitrogen plus a photon, and then this nitrogen is going to beta decay back to a carbon. Let's see, it beta decays, so that gives me, I lose a proton, so that gives me an electron plus an antineutrino. Is that right? No, it's the other way. Yeah. So that's what I get for thinking before me. Okay, so the neutron, the nitrogen then beta decays back to a carbon. Then we take the carbon and we pack on another hydrogen, and this gives me nitrogen again. Does that give me a neutron? It does. This nitrogen is stable, so if we pack on another hydrogen, then we get to oxygen. Yeah.
Is that first a positron and a neutrino?
This?
Yeah.
This is a positron and a neutrino.
Okay.
This goes to oxygen plus a photon. This is unstable, so it beta decays. Back down to nitrogen 15. Oops, sorry, did I write that right? Oxygen 15, beta decays to nitrogen 15 plus an electron plus a positron and a neutron.
And like the beta decay in the PP chain, does that also take in an electron on the left side?
No,
No.
it spits out a positron.
Okay,
Those are equivalent. You can either take an electron or spit out a positron.
gotcha.
So then we take this nitrogen plus another hydrogen, and we're left with oxygen 16. And then the oxygen 16 let's see.
And is that plus a photon?
Oh, I'm sorry, I did that wrong. Looked at the wrong thing. The nitrogen 15 plus the proton goes back to a carbon 12 plus an alpha particle. So this is the first way that it can finish up. Yeah.
In the oxygen stuff, right above that line, that takes in an electron, right?
No, he said it spits
No,
out
it
a
spits out a
positron.
positron.
But it doesn't take one in.
What?
It doesn't also take one in for
Huh.
that to happen?
No,
No,
it spits out a positron.
That's
The neutron beta decays.
it just does.
Yeah.
The neutron beta decays or the proton beta decays?
Oh, no, sorry, I convert a proton to a neutron, right, the neutron goes away. Yeah,
Okay.
so it's an inverse beta decay. All right, and let's see. And if you write this like a power law, then you can say that epsilon CNO goes like density times temperature to the almost 20. And then there's some factors of X and stuff in there. So what does that mean? What does that mean about where these processes exist in the star? So I have some temperature gradient, right? And these processes fall off. One of them falls off like t to the 4th, and the other one falls off like t to the 20th. So which one's going to stop first? The CNO is going to stop first because that's a much stiffer knob. So as the temperature goes down, the CNO cycle, the CNO energy rate goes down very quickly. So CNO is good for massive stars right at the center. PP chain is good for all sizes of stars, still at the center, because it falls off like t to the 4th, which is still pretty far. Yeah, pretty fast.
All three of these processes go at the same time, right?
Yeah, everything's going on at once. Okay, I think that's all I got for the day. Let's see, is there any other thing that I want to talk about? Nope. No, that's it. Okay, does anybody have any questions about this? This ends what I'm going to say about, oh no it doesn't. I got a couple more things that I'll say on Tuesday, and then I'm going to start massive star evolution and the endpoints. So we're going to get out of this chapter and we'll get to the somewhat more tractable stuff. Well, more tractable for here. Anybody have any questions? Everybody happy?